Hello, I'm Pierre-Alain Frémont, working for SBM Offshore as a hydrodynamic engineer, and in this GIP I perform the calculations for the TLP floater. And I think we can go to the next slide. So, as explained by Tanguy at the introduction of the numerical simulation part, we perform several cases. Some ship-to-ship transfer, like Melissa just presented to you. We also perform the cases with a blade, ship-to-ship transfer, and a blade before integration to the hub system. This case has demonstrated that both floaters have similar behavior, and that's why we can conclude for the first case that this difference is not linked to the floater itself, but mainly to numerical simulations. And now we'll introduce the last case, which is a hub replacement. So interest of this case is to not have this ship-to-ship transfer, which brings some uncertainty on the tugger lines, on the pendulum motions, and on the ship itself, on the crane. So the system itself is a self-hoisting crane, which is mounted on the mast of the floater, of the turbine. So you can see on the left, we did not represent it. This is a schematic, but we did not represent it in the numerical model, the connection to the tower itself. We don't focus on the structural integration, but we focus on the relative motions of the hub, which is lifted. So the hub weight is about 190 tons, and in this model, we multiply the drag of the system of the tower by 2 to account for the drag due to the crane, and same as for the first case, we did not account it for the second order wave force on the floater. The sea states which have been studied are exactly the same as previously, as you can see on the right. Next slide. So for this case, we also perform two sub-cases, one with tugger lines and one without. I will just focus on the second case with tugger lines. So as you can see, comparing the two plots for the Volturn US and the TLP, we have some quite similar result as well. And there is no preferential direction. You can see that there are some success, low rate of success for this case, but there are some success in almost every direction for small HS. And except for quarter Cs, there are some failure case also for the periods around the pendulum motion, which is about 7 seconds. So for this case, no major differences between the two floaters. A bit higher rate of success for the TLP, but this is very marginal. Yes, next slide, please. So on the criteria we have looked at, we focused on the distances at interface. So we looked at an offset horizontal and vertical because for this tape we considered that we want to keep the hub in front of the nacelle for integration. So we want to have a limited offset. And at the same time, we don't want the contact because we need to control the package. So there is also a criteria on a limited distance between the hub and the nacelle. And this is this last criteria, which is the main limiting criteria. So you can see on the diagram, the blue bars are for the semi-sub and the green bars are for the TLP. And so there is a higher rate of failure for the semi-sub on the horizontal distance, but a higher rate of failure on the vertical distance for the TLP, and as well, let's say 5%, 10% difference for the offset, but this is a high level of failure. Also, we managed to control the tugger line tension for the TLP, and not for the semi-sub, but as explained during the introduction, we have some different modeling on the tugger lines, which may explain the differences in results between both floaters categories. So we need to consider that the results are not due to the floater itself, but probably more due to the simulations and the tugger lines modeling. And if we go to the next slide, so this is the global rate of success on the 234 cases. So you can see that without tugger lines, there is about 17% for the Volt-On US and 10% for the fast forward floater. And when adding the tugger lines, it doubles the percentage of success for the TLP, but it reduces for the Volt-On US. The reason for that is some modeling issues with the tugger lines, creating some kind of excitation of the package, and which amplifies the motions, and so reduce the distance, the offset, and create some failures. So for this case, what we can conclude as levels of improvement is that the way we model it is probably not sufficient for this kind of package, this kind of maintenance operations. We will need to model more complex tugger line system, and also to include some kind of stoppers and guide in the operations. Also, maybe the criteria we have defined for this case are not as accurate as for the previous case, and we will need to redefine the distances for interface or for contact. And the last point is maybe the methodology we applied for this case, which is to simulate a 3-hour states and to calculate design values on this. Maybe it's not appropriate for this kind of simulation. Maybe it was sufficient for the ship-to-ship transfer, but maybe for this kind of transient operation, we will need to model the transient step itself. So now if we go to the operability, so the approach is exactly the same as for the MC air deck. So here this is for the Mediterranean Sea, and we can see as for the wind roses before that there were no predominant direction. We can see the percentage of success is more or less around 30% for all direction, with a bit of better results in southeast direction, which is when the vessel is the floater is facing main wave direction. Then if we go to the next step, next slide, yes. So on the scatter diagram, you can see there are quite a lot of red dots because there is quite a high failure rate. This is just so the representation. The good point is that for this Mediterranean Sea site, we have quite some small periods and small wave HS. And you can see, for instance, for the northwest direction, that the case with the background in dark, which is the most probable case, is a success for both floaters. And if we compare, yes, both floaters, so in that case, there is a better success for the TLP for the periods at 7 and 9 seconds, which are managed for small waves in that case for the TLP. But that has a low impact on the operability results because you can see we are going from 11.18% for the semi-sub versus 11.21% on the TLP. So the two sea states which are not succeeding for the semi-sub have a very low occurrence percentage. And if we are looking at the season for the main direction, here we can see a seasonality with more favorable periods during the summer with higher percentage of success, about 50% between June and August. and the worst operability success during the winter, which is the period at which we have the highest states. Next slide, please. On the other side, for South Brittany, this is much more complicated to conclude because the sea states are within the excitation. Sea states are higher in periods than in wave 8. And for both floater, we have quite very small, about 1-2% of success of operability. But as explained before, this should not be considered as a definitive result because this is probably more linked to the numerical simulations we did for this project than on the solution itself. Looking at the scatter diagram, so we can see here that in that case, the black cell, which is the most probable direction, is a failure, which explains the differences. And here the sea states, which are failing for the semi-sub and succeed for the TLP, are contributing to only 2%, which is the highest success rate we have. So I think, yes, in terms of seasonality, the percentage of success is so low that it's also complicated to interpret. So yes, in that case, we should define some more precise operational limitations to refine the results and probably increase the operability. As explains the current simulation process. So we have a 3-hour sea state. We divided into 10 minutes windows for which we keep only the maximum value, and the design value is the average of those 10-minute maxima, and probably a transitory state transient simulations to model the contact would be more adapted for this case.